I'm Darren Llewellyn. Welcome to another episode of MyToolboxTV. Today we're going to talk about Ohm's Law. Now, don't worry, it's not all going to be about math. Ohm's Law's main use is to show you the relationship between the fundamental quantities: current, voltage, resistance, and later we'll talk about power. Let's take a look at Ohm's Law. Ohm's Law. Yeah, it's a mathematical formula, but it will show relationships between the four fundamental quantities. The first three quantities we'll talk about with Ohm's Law right now are voltage, current, and resistance. When you see Ohm's Law written like this, sometimes it'll be a circle instead of a pyramid like this, but the E stands for voltage. Anytime you see that in a formula, electromotive force. The R is resistance. Pardon my penmanship. And I is current. Now, there's a couple R's there. If you change one of these fundamental quantities in a circuit, it will change some of the other quantities. Okay? And the way this formula works here, let's say that you want to find current. You're trying to calculate current in a circuit. The way you do it is, here's current. You would divide voltage by resistance. If you wanted to find resistance, divide voltage by current. It'll tell you what the resistance is. If you want to know the voltage, multiply current times resistance. Now let's look at these in a circuit. As you might remember from earlier videos that we had, voltage is the pressure in a circuit. Voltage doesn't move. Voltage is applied to things. Voltage makes current move, causes electron flow. So voltage applied to a circuit will cause current to flow, the moving part of electricity. Voltage, of course, is measured in volts. Current is measured in amps. Resistance, as you might recall, is the opposition to current flow. It opposes current flow. Let's see how all these work together in a circuit. Resistance is measured in ohms. That's a pretty dandy symbol there for the Greek letter omega. Here's a battery. Here's a resistor. Okay? If it's a complete circuit and the battery is charged up, and as you might remember from earlier discussions, a battery that's charged is unbalanced. It's got a surplus of electrons on one side, and it's very positive on the other side. Electrons being negative would be the negative side. So when you have this situation, complete circuit, and there is voltage applied from the battery, current will flow because you have a complete circuit. About the only thing that current needs to flow is voltage and a complete path. Okay? So the voltage is applied from the battery. The current flows through the resistance. The resistance opposes current flow. And then its properties, what happens is heat is created in the form of power. And we'll talk about that later. Now, this current flowing, which current is measured in amps, if you increase voltage, if you increase the voltage, more current will flow because resistance is a fixed number. Let's say that our resistance is 10 ohms. Okay, we have 10 ohms of resistance. 10 ohms of resistance, and let's say that we've got 20 volts applied to the circuit. How much current would flow? Ohm's law can tell us. Ohm's law can tell us. Let's say we want to find current. According to our pyramid here, we would divide voltage by resistance. So 20 volts divided by 10 ohms gives us 2 amps of current flow. 2 amps of current flow. Now, let's change one of the fundamental quantities. Let's say that we increase the voltage to, say, 40 volts. We leave resistance the same. What happens to current? Well, now at 40 volts divided by 10 ohms, now we're looking at 4 amps instead of the 2. So use Ohm's law to help you understand the relationship between the fundamental quantities, because that's what's really important. Now, what happens in this circuit if we leave voltage at 40, yet we change the resistance? Let's double the resistance up to 20. Okay? Now we've got more resistance. Well, same formula. Now it's 40 volts divided by 20 ohms. And what's that give us? About 2 amps. Okay? So the relationship can be shown by Ohm's law. And it's so important that you understand that for everything you might get involved in, with troubleshooting, everything. More voltage on the same resistance means more current. More resistance to the same voltage means less current. You can also do things like, let's say that we happen to know we've got 40 volts, and we know that we've got 4 amps, but we don't know the resistance. We can calculate that too. We can calculate that by, we know amps and we know volts. So 40 volts divided by 4 amps, well, that gives us that 10 we had earlier. You can always find the unknown quantity. And sometimes we may not know voltage. We may know our other quantities. You know, we may have, let's say, 8 amps and let's say 20 ohms. We can easily figure out what that is. So if you don't know voltage, and you know amperage because you measured it, and you know resistance because you either measured it or it was written there, and you can find the voltage. You can find any quantity that you don't know. In this case, 8 times, we take the current times the resistance, 160 volts. So it shows relationship, and we can find unknown quantities. You just can't imagine how often knowing this fundamental relationship applies to everything you do. You know, in whether it's troubleshooting, circuit design, or just trying to explain to your mother-in-law why all the space heaters plugged in trip out the circuit breaker. All kinds of things like that. Wow. Our Ohm's law formula got a little more complicated, didn't it? Our little triangle is expanding in this great big pie thing. What we've added is power. We started out with the first 3 fundamentals, voltage, current, and resistance. Now we're going to add power. If you add a 4th fundamental, you get all these other formulas. The way it works is just like the other one. If you want to calculate current, these are the 3 formulas that will calculate current for you. This is the simple one that we just did a while ago. It's voltage divided by resistance gives you current. The pressure divided by the opposition gives you this much flow. Now if you add power into the current equation, it's power divided by voltage gives you current. You can also do it with resistance. Honestly, not one I've used very much, but it would be the square root of power divided by resistance. If you want to calculate power, what is power? In the simplest form would be voltage times current. Anytime you multiply voltage times current, you're going to get power. One that's very commonly used is this one, I squared R. You might actually hear that term in motors and inductive loads. You'll hear a term called I squared R loss. And I squared R loss is the heat that you feel built up on an electric motor, or it's a lot of the heat anyway. It would be current squared times resistance of, in this resistance in the case of electric motor, would be the resistance in the motor winding. That's the I squared R loss. That heating, it's a loss because you're not getting any work from it. So that would be one of the formulas for power. If you want to calculate voltage, voltage would be power divided by current will give you the voltage. Then, of course, there's others. There's square root of power times resistance. I've not done that one much, but there's also this one, which might look familiar. It's the one we did a while ago. It's current times resistance gives you voltage. Now, all these formulas are in their simplest terms. When you start adding other things into a circuit besides just resistance, Ohm's law gets more complicated. When you start adding things like three-phase power, wow, now it gets even more complicated. So these formulas work. They help you understand the general relationship between power, voltage, resistance, and current. And they are the building blocks to all other formulas that you may see. Like in a little bit, we'll take a look at a formula for the how to calculate the current of a three-phase motor. And it looks very complicated, but in its simplest terms, when you look at it, it's just Ohm's law. It's this one right here. It's power divided by voltage. But there's a lot of other stuff in it. Let's take a look at that one. Now, let's look at a formula for calculating the current for a three-phase induction motor. Now, if you look at this, it looks kind of full there, all kinds of stuff in it. The top of it, horsepower times 746. 746 is a constant because there's 746 watts of power consumed per horsepower in an electric motor. So what we're doing here is converting horsepower to wattage. So the top of this formula becomes power. Okay? So forget this. Now we got our power. The bottom side of the formula starts out with voltage, E, times the square root of 3, because it's a three-phase motor. So voltage times the square root of 3 times efficiency of the motor times the power factor of the circuit. We'll get into those things in another video at another time. But basically, the entire bottom side of this formula is to get us a true number of the voltage applied to this motor. Okay? Now, look at this. It's power divided by voltage gives you current. Even though the formula is big and scary looking, that's not the situation. It's got its roots in this little formula right here. Power divided by voltage equals current. So these things come up like this all the time. So a lot of the big scary electrical formulas really apply Ohm's law thinking to it, and you'll understand the relationships to it. You know, you'll be able to use Ohm's law throughout your career in electrical work or electronics because it's one of the fundamental building blocks. It's like in football, knowing how to block and tackle, or in basketball, knowing how to dribble the ball. You got to know this stuff, and knowing it, you can figure out other things. Like I'll never forget one time I was a student just beginning to study electricity and electronics, and I was trying to figure out, you know, I was just learning Ohm's law. How come in the power lines that the power companies use that they kick the voltage way up to 345,000 volts or 500,000 volts, but this makes the current go down? And it didn't make any sense because I'd just been taught Ohm's law. And what I knew was that when you increase voltage, current goes up. Well, one thing I didn't know is, at the time anyway, is that in a transformer is able to maintain power at the same level. So as current goes through a transformer, power doesn't change. So if you kick the voltage way up, and the power stays the same in the circuit, current would have to go down. And Ohm's law is how I figured that out. So that was just an example that I had as a young student going through this stuff. But you will find those kind of things all the time. You will find things that don't make sense, but if you sit down and think about the relationships with the fundamental quantities and how Ohm's law can show us those relationships, then it'll make more sense. Thanks for joining us for another episode of MyToolboxTV. Appreciate you coming. Hope you got a little better understanding of Ohm's law today. And we'll see you next time.